What I want to try doing in this video is to give you some sort of intuition as to how your solver is able to solve for different configurations of your finite element analysis. Now, this remains true irrespective of which software you're using for FEA. It could be ANSYS, it could be Comsol Multiphysics, it could be any software you're utilizing for finite element analysis. There's a definitive framework around which your solver is able to solve and produce solutions. And usually for those things, you'd also want to look at your convergence plot. Now, before I talk about convergence plot, I want you to have some intuition as to what an FEA is, right? When you look at an FEA, a finite element analysis, you would come across two terminologies. Now, the first terminology you'd come across is a solution space. Now, for any configuration, you see this entire illustration here is your solution space. Now, within your solution space, there are different domains, right? Now, in our previous experiment for eigenfrequencies of cantilever beam, our cantilever beam is one domain which is present in the solution space, right? And the way in which the solver solves for the eigenfrequencies for this domain is by dividing this domain into what you'd call as elements. Now, if you know when I generated mesh, you saw that the entire cantilever beam was divided into subblocks, right? And since we used the swept mesh, the subblocks were cubed in structures. They were somewhat of a cube, right? Now, if I'm going to illustrate the difference between a normal mesh and a fine mesh. Now, you see in a normal mesh, this entire cantilever is divided into three different elements, right? There's element 1, 2, and 3. Now, these three different elements have 16 nodes. Nodes are nothing but those circles you see, those black circles. And if you count them up, there are 16 nodes for these three elements domain. But when you look at a 6-element domain, where this entire cantilever beam is divided into 6 elements, you see that the number of nodes dramatically increases from what it was in the 3-element domain. And this becomes important because what you have to understand is your solver basically solves at each of these nodes, and what happens eventually is the solutions at each of these nodes are basically integrated to give you the final solution, right? So more the number of nodes means more the number of solutions which get assimilated, and then you would obviously have more accurate results, right? So that is why you want to use more number of elements or more number of meshes. So the finer the mesh is, the more the number of elements is, and the more the number of nodes, which exponentially grows is. And more the nodes you have, more the number of calculations which are assimilated, and more the number of calculations which are assimilated, the better your final results are going to be. This is essentially the premise of a finite element analysis, right? Now, what I want you to understand with this is your solver is going to solve at these different nodes to produce or assimilate it into a final result. Now, the process of your solver doing this happens in iterative steps, right? And iterative steps. So it's going to do first iteration, and then it's going to go next iteration, and slowly it's going to arrive at the solution. Now, the way at which it arrives at the solution can be visualized in a convergence plot. Now, the convergence plot physically implies how your solver is able to arrive at the required solution. You'll be able to visualize if the solver is able to easily arrive at a solution, if your solver is struggling, if your solver is stuck, being able to analyze a given step. And then based on all those different things, you'll be able to conclude on the validity of solution based on your convergence plot, right? Now, there are a few terminologies you have to understand when you talk about convergence plots. One is obviously the iterative steps. This is the number of iterations your solver is going through before it arrives at the solution. But when you talk about error tolerance, this is talking about the difference between the expected value and the calculated value. Now, this difference is what you'd call as the error tolerance. Now, Comsol expects the error tolerance to be below a certain value, below a certain threshold, sorry. And if it's below a certain threshold, the solution is met. So basically, you'd be able to adjust the tolerance, and you can adjust the tolerance based on where you're utilizing this value at. And usually, the convergence plot for static analysis looks something like this. Usually, if your solver is converging linearly, it means it's taking lesser number of iteration steps, and it's able to arrive at the expected threshold sooner. Your solver is able to easily solve for the solution. But if your solver is exponentially decaying, it means that it's struggling to reach the expected error threshold, right? And usually this happens if your mesh quality is poor, or if the time step, if you're doing a time dependent analysis, your time step can be really large. So if your time step is really large, or your mesh size or quality is really bad, then your solver is going to struggle and eventually is going to arrive at the solution, but it's going to take some time. Now, usually, you'd sometimes see oscillations in the plot, your convergence plot. Now, when you see oscillations, your solver is failing to reach a steady state from which it can arrive, or reach a solution from. So this is going to cause a problem because your solver is never going to converge or reach that lower error threshold, because it's continuing to oscillate and it's going to exhaust itself, and you're simply going to waste compute. So you would have to basically spot this early on and stop the process to either resolve it by increasing the mesh size, or you can decrease the time step. You can do a number of things to solve an oscillating convergence plot, but we will explore that later on. What I want to do right now is I want you to visualize the convergence plot we had for the previous experiment with the eigenfrequencies. You see the convergence plot is linear in nature. This is what we expected. It's reaching the convergence really soon, and the expected tolerance for this study was actually just 1e to the power minus 6. So we did not really want um, or it was 10e to the power minus 7 to give a more clear answer. But we've expected the tolerance quite low. But you see the tolerance here, the error estimate here has gone even lower. And the reason for that, if you go to the log file here, you see that in the first iteration itself over here, 5 of the 6 modes. So have in eigenfrequencies we solved for 6 modes. We have seen that 5 of the modes have converged with the error estimate which we initially gave. We gave the threshold of 1.01 or 1 times e in the power minus 6. All of the 5 solutions have converged in the first iteration step itself, but one of the solutions was not converged, which has been converged in the next step. But the next step reduced the error estimate even more, which is all right. And since it's gone below the required tolerance, in the second iterative step, all the 6 modes have successfully converged. So this what essentially implies is the tolerance which we're setting is the error estimate. So the iterative step should reach that error estimate for that solution to be valid. Now I can make this tolerance high if I don't want a very accurate result. This will help the solver solve even more quickly. And if my given application does not require that amount of tolerance, I'm more than good with it, right? Now sometimes it takes the solver more time, it exponentially decays, it takes more number of iterations. Now at those times I can increase the number of maximum iterations here. This allows me to solve for more complicated variables. Usually that's not the case. Now to make sure that your solver doesn't struggle, make sure your mesh's quality is extremely good. Because now I'll show you the convergence plot for a mesh quality which is not as good, right? Let's do, instead of an extremely fine mesh, let's do a coarse mesh this time. And for a coarse mesh, I will try running the same study which we computed the last time. And I want you to try visualizing. Now it's going to it's going to take its time, but I want you to try visualizing the convergence plot for this given study. You see the convergence plot is not as accurate. It's a little jagged. It's not as clean, and it's still converged to the second plot itself, but it's not as linear as we want it to be, right? So you see it is not as steep. It has reached error estimate of something even smaller, and the final has somewhat reached the error estimate it previously reached, but it's not as accurate as you would have seen with a more finer mesh. So using a more coarse mesh would cause something like this, or it would cause a more exponential for a more complicated system. And you don't really want that to happen. I could probably try to illustrate this even better by using an extremely coarse mesh just to show you what it's going to look like. Now, if I'm going to compute with this mesh right now, the same solution, and I show you the convergence plot for it, you will notice that the convergence plot is even less ideal. And this isn't something you want. You see that the solution is reaching an even lesser estimate at the first step. This isn't something we really want. And if you see the log files for this, and I can check the log files over here, you see that the same number of solutions are reached, but the error estimate is not as good as it was in the first case, and the same is in the second case as well. And this plot is not as good as the other plot. It's taking the same number of iterative steps because the complexity of the system is not very high. But you see the convergence plot clearly tells you how the solver is struggling slightly to solve the same solution, even if it is reaching the solution effectively the same way with the higher mesh quality. So yeah, this is how you'd analyze the convergence plot. How to improve the convergence plot is to just improve the mesh quality, or work with the different time steps, or to increase the number of iteration numbers, or to basically decrease the tolerance even. Now, these are different things you can do to help the solver solve better, right? Another topic I wanted to discuss is something called as segregated solvers. Now, what happens in a very complicated system is you would have multiple variables, right? You'd have multiple variables which cannot be solved in a single iterative step. If you have to solve it in a single step, it might take a very long number of iterations for your system to reach that threshold error estimate, right? Now this takes a lot of compute, and not only does it take a lot of compute, it's more about the amount of RAM, or the amount of virtual memory which it's going to take. Now, for something as simple as eigenfrequency, the amount of virtual memory that was utilized is nearly 2 GBs and around 1.3 GB of physical memory. Now, when you start to consider this for a more complicated system, this could take anywhere from 10 GBs to 100 GBs, even based on the complexity of the system. And sometimes your system might not really have the physical resources to allocate or accommodate for that. So in modern FEA softwares, we have something called a segregated solvers. So what these segregated solvers do is they divide the complex multivariable system into independent variable subsets. They divided it into subsets. Now these independent variable subsets are individually solved, and you see there's a convergence plot for that. It reaches the threshold or error estimate threshold, and once it's going to reach that, it's going to take that variable one value as an input for the second variable calculation, and it's going to iteratively solve for that as well. So the number of iterative steps for each segregated solver iteration is very less. That means the physical amount of RAM, or physical amount of virtual memory required for that system, is drastically reduced. So your computer is able to simulate a very complicated system by dividing that system into smaller subsets and calculating individual variables sequentially. And you'd see multiple of these plots like this. And sometimes for CFTs, that is why you see multiple values like this, multiple plots for the convergence for things like CFT or things like complicated FEA analysis. You see multiple convergence plots, and when you see these multiple plots, it's almost always that your system is using a segregated solver, and this is very helpful. Now, one last thing I wanted to discuss is how you can help your solver solve a given system. And the number of different things you can do, obviously, as we've discussed, is you can improve the mesh quality to help the solver reduce the number of iterative steps. This helps the solver solve more faster, reach the error estimate more faster, and it's overall really good. What you can also do in time dependent study is to reduce the time steps. What this does is it helps to calculate for changes even more finely. So what happens in a time dependent study is obviously your physical quantities are going to vary with time, right? But if you're going to look at values from really large time steps, the physical quantities might sometimes look discontinuous, right? It looks very jagged, and that's not very nice. But if you increase the time step, what happens is you then know exactly how your physical quantities are changing with time, and this looks more continuous and jagged continuous than this jagged line which looks somewhat discontinuous in nature. So you want to reduce the time step to help the solver solve better in time dependent studies. And sometimes increasing the number of iterative steps in complicated systems also helps this solver by giving it more time to solve, even if it's going to struggle. Sometimes you could also decrease the threshold of tolerance if you don't want the solution to be as accurate to help the solver solve faster. Sometimes you might want to resort to the segregated solver, which we previously discussed, where complicated systems can be reduced to manageable subsets, which can be solved with lesser RAM of virtual memory requirements. And sometimes, if your solver convergence plot is oscillating, you might want to physically identify that and stop your plot, and then improve your mesh quality or decrease time step or troubleshoot your problem instead of wasting computation. Because if your solver's convergence plot is going to oscillate, you know you're never going to arrive at your error estimate or physical solution. And these are little things you can do to understand how the solver is solving for solutions, how you can help the solver, and how finite element analysis as a whole is working in any given FEA software. So it's always a really nice skill to learn to read your convergence plots. With that, I think I'm going to end this video. Another small cookie I wanted to do is, last time I couldn't really show you animations for the eigenfrequency plots because I didn't really have the time for it. I'm going to show them to you right now. And the way to do that is, as soon as you've added an animation, you can click on the button here to play the animation, and that's going to basically play the animation. This is the torsional displacement mode for the eigenfrequency, and this is one of the animation. I can show you another animation. We can go to the mode shape and we can change this to, let's say, let me change this to axial. I want you to try visualizing the axial mode. We come to animation here and I can play, and you see the axial mode compresses and expands. This is how you can visualize for animation. It's always nice to visualize your plots. It sort of gives you a lot of intuition, and you can try this by yourself. Hopefully by the end of this video I could do some justice in helping you understand how to read convergence plots, how to understand how FEA works, how segregated solvers work, how solvers work for that matter. And these are things I hopefully think you could understand better by practicing or trying or experimenting yourself. If there's any other feedback or doubts, you can let me know in the comment section. I hope you're having a nice day. Bye bye.